Hi, I hope till now you have been enjoying the course of Introduction to Astrophysical Fluids. So in the previous discussion, we were discussing of the derivation of real fluid equations. Today, we will study a very specific limit of real fluid equations, which is a very trivial limit actually. So it is called the hydrostatic limit. Hydrostatic we all know from our school days. So today, maybe this is a good occasion to revise all these things. So if you want to, think a bit in a systematic way, that whenever in physics we talk about a model or something, how to really verify. So basically one very simple way to check. Okay, so this is not always easy to check whether our model is a good one or is a model is a, correct one in the sense that whether the model there is no there is no fault, or there is no how to say inconsistency. Okay, so one specific way to check that is to check its different limits. If we succeed to reproduce our known results for that specific limit, then it is already a very good indication that there is there is a good chance that our model does not have any serious problem, okay, or serious inconsistencies. So here exactly this is one of the objectives with which we will discuss a specific limit of hydrodynamics, and that is the hydrostatics. That means we consider a fluid is at rest. Okay, and for that we will of course start with our real fluid equations, which we derived in the last discussion. So this is the continuity equation: del rho del t plus divergence of rho v is equal to 0. Okay, and then you have del v del t plus v dot nabla v is equal to minus gradient of p by rho plus g. So g is the gravitational acceleration or any body force acceleration. Okay, plus this is the whole term due to the viscosity. Okay, and finally this is the equation for the evolution of the internal energy epsilon, and we can show that this is nothing but rho del E del T plus V dot nabla del epsilon, okay, del epsilon del T, of course, sorry, plus V dot nabla epsilon is equal to divergence of K times gradient of T. So this is the term of the energy transport by conduction, okay, and this is the term which we had, also we had also in the ideal fluid case. This is the term which is minus P times divergence of V. Okay, so one simple thing is that how to reach the limit of hydrostatics. So it simply says that first of all, as the fluid is at rest, so let's say the fluid is in a container, okay, confined in a container, and it does not move. So the fluid velocity v is equal to 0. Okay, so the bulk velocity or the fluid velocity or the macroscopic velocity is 0. Now you think that, it does not say that the kinetic velocities u, they are 0. They are still non-zero. It is only the average velocity which is 0. Again, another element to designate the static case is that there will be, for every variable, okay, whether it is rho or it is v or it is p, there should not be any explicit time dependence. Okay, so these two things give us the limit of hydrostatics. Okay, so then you can easily see this equation is trivially satisfied, because this is then 0 and also 0. V is there, so it is 0, and del T is 0, so 0 is equal to 0. So we don't worry about this equation any longer for hydrostatics. Now what about this? So of course this term is 0 because of both reasons. V is 0, del T is also, del T of this is also 0. So V is 0, V is 0, V is 0, V is 0. Okay. So if you have this type of case, then you have only the surviving terms to be minus gradient of P by rho plus G. Okay. And that's exactly what we have written here. So this is the momentum equation for hydrostatics. So this is the force balance equation. And now you can recover your school days message of hydrostatics that the net force acting on a fluid at rest is nothing but the force due to its pressure gradient. Okay, so that is its body force basically. So remember, when I just was describing the real fluid equations, I said that G is the acceleration due to gravity, and then I said, well, but this is acceleration of any body force. So actually, when the system is at rest, okay, yeah, if the system is at rest, basically, one thing is possible that, what happens, basically this body force, whichever, maybe the system may be also in the effect of this, how to say, gravity. Okay, then this gravity will be exactly equal to this one. Okay. So the acceleration due to gravity will be exactly equal to the acceleration due to the pressure gradient force. They will counterbalance each other. Okay. So and that is the case of usual fluids confined in a container in everyday cases, because they are always inside in a gravity field, right? The terrestrial gravity. Okay. And for that, so the body force is G, that is true, but the body force is also equal, due to this balance, is also equal to the gradient of the pressure. Okay. Now what about the simplified form of this evolution equation? This will become again 0 because del T is there, and V is there 0, V is there 0, so this term will be equal to 0. So that is the simplified form of the evolution equation of the internal energy. Okay, so finally we have these two equations to be the governing equations for hydrostatics. Now you see, of course, we made del T 0, so nothing is evolved, nothing is evolving in time. So we only have the equations have changes, but they are only spatial changes, gradients, right? So that is something to understand. In hydrostatics, the explicit time, by the definition of hydrostatics, we do not allow the explicit time variation or evolution of something, because we only assume that the evolution is done only by the virtue of the flow. Okay, if the flow is not there, then there is no evolution. Okay. Now in the case of one-dimensional case, we have dp dz is equal to minus rho g. That is nothing but the one-dimensional simplification of this equation. Okay, so gradient of p will simply be then dp dz, and that will be equal to minus rho g. Why there is a minus sign? Because g is acting downwards. Okay, and we are considering our z direction to be normally upward direction. Okay, vertically upward. Okay. For incompressible fluid, if we now think of, let's say, not only any fluid at rest but liquids, for example, at rest, let's say a glass of water. For incompressible fluids, rho is constant. So when you integrate, basically this is a very simple integral. So dp is equal to minus rho g dz, and rho g, both of them are taken to be constant because g is the body force acceleration. So it's a gravitational acceleration which can also be reasonably assumed to be constant. Okay, and then you just integrate, it will give you P is equal to some constant of integration P0 minus rho g z, and P0 is nothing but the pressure. Okay, so P0 is nothing but the pressure when Z is equal to 0. So this is the base level pressure. So it simply says that when you start at this level, Z is equal to 0, your pressure is P is equal to P0, and when you are just changing your Z either upward or downward, your pressure will be changed to P. Okay, now if you are changing your Z in such a direction that your Z's are negative, then basically you will see that this part is getting bigger because Z is negative. So P0 plus some rho g and the modulus of Z or the magnitude of Z. So finally it will have a greater value of pressure, and when you are going upward, so your Z is positive from the reference level, then your pressure will be less. Okay, that's why we can again remember our school day message that the pressure of a fluid at rest increases linearly with depth. Of course, here the fluid should be very much incompressible. Okay, so incompressible. So I can just make a note over there, fluid, liquid. Okay, it's liquid actually. Okay, now we take the simplest compressible case. So that was the incompressible case. Okay, now we will see what happens for the simplest compressible case. Okay, so once again we are always in the hydrostatic regime, and we are talking about a compressible case with a very simple closure which is called the isothermal closure. Sorry, isothermal closure. That means T is constant. Okay, if T is constant, then you know from kinetic definition P is equal to n kBT, and n can be written as rho by m. So finally you will have P is equal to rho kBT by m. So now if you just remember this equation, dP dz is equal to minus rho g, then what happens, you can now write dP dz is equal to, okay, is equal to dTz of, instead of P you can write the whole expression, and kBT by m is constant. So this is constant because T is constant, comes out, and this is nothing but kBT by m times d rho dz. Okay, and that is equal to minus rho g. That's it. So if we solve that, so you can see from here, so you just have to solve this simple equation, and if you solve that, so everything is constant over here, this is constant, and so you just have to say d rho by rho is equal to minus some constant times z, and if you do that, you know this will be nothing but a exponential law for the density as a function of z. Okay, we are always in one dimension for simplicity. Okay, and this is simply rho is equal to some rho 0 e to the power minus mgz by kBt. So where rho 0 is nothing but the density at z is equal to 0. Okay, at reference level. So evidently here we can see, just like pressure, density also decreases but in a different way. So pressure was decreasing in a linear way for incompressible fluid, but for isothermal fluids density is decreasing but exponentially, okay, as Z increases. Okay, so these things we also may have learned. Okay, so all these things are very known results. Okay, now we can discuss, so till now we have discussed one case of incompressible fluids, that is the liquids, and one case for isothermal fluids. For two cases we know that the only useful or necessary equations are the equations of continuity and equation of momentum. But in our current hydrostatic case, equation of continuity is trivially satisfied always. So equation of momentum is the only equation, okay, to be read. So energy equation, to be very honest, is redundant to constitute the dynamical theory for incompressible and isothermal fluids. There is another class of fluid which is, you know very well, barotropic fluid, where P can be written as, once again this is confusing, it's small p always, small p. P is written as a function of the density only, okay. Under that condition, the fluid is known as barotropic fluid, and for a barotropic fluid, that will be the same thing. Only we should be worried about or concerned about the momentum equation and not the energy equation. But then what will be the equation? Well, the basic vectorial equation should be the same. Okay. Gradient of P by rho is equal to G. Then now we will do something interesting, and that's people in general do when they are working on stellar structure. Okay, so you can directly write from here. Okay, so what they do, they use this type of equation to determine the stellar structure of a polytropic gas. Okay, of a polytropic gas which is self-gravitating. Okay, to study its equilibrium. So one very the traditional way is to take the divergence of both sides. So you will have divergence of gradient of P by rho is equal to divergence of G. What is the advantage of taking divergence? That finally you can use Gauss's law of gravitation to find the equality between divergence of G is equal to minus 4 pi G rho. Rho is the density. So here you have P, which is a function of density. Here you have rho, and here you have rho again. Okay. So finally what happens, that you don't have to think of the field, the body force field again. So you just have everything in terms of the fluid density. Okay, and the pressure, but pressure is also in terms of the fluid density because this is a barotropic fluid. So now if we assume the closure to be P is equal to K times rho to the power gamma, although in some literatures you can see another different type of writing. So they sometimes write in astrophysics, rho, it's rho to the power 1 by 1 plus n, and they call this n as polytropic index. But finally this 1 by 1 plus n is nothing but this gamma. Okay. So if we now assume P is equal to K rho to the power gamma, where gamma is our polytropic index in fluid dynamics in general, then substituting this in this above equation, so you can just substitute this this one here. Okay, if you do that and finally you just write, so from this equation to this equation, I did not I just skipped that. So this equation to this equation, basically one can obtain when you are assuming spherical symmetry. Now thinking of a polytropic gas, a self-gravitating gas, the most natural thing to assume is that is a spherical symmetry. Okay, so the divergence is given by, in spherical symmetric case, is given by 1 by r squared ddr of this thing. Okay, so that is the divergence operator. So the divergence operator basically includes this part. Okay, and what is inside, that is dpdr. So gradient is nothing but 1. So gradient of P is nothing but dpdr. Okay, and 1 by rho gradient of P is nothing but 1 by rho dpdr. So when you write the whole thing in terms of, in case of spherical symmetry, you will have this thing. Okay, so finally this equation is equal to this equation. Okay, and when this is written again, so I said in advance that replacing P by this, and then finally writing this everything in terms of the non-dimensional quantities. Okay, that you can do by saying that R is some, is equal to some A times R0, this type of thing. Okay, if you do that, and you can also define some non-dimensional quantities for rho corresponding to that is xi. Okay, if you do that, finally you will be given an equation which is known as the famous Lane-Emden equation. So Lane-Emden equation finally gives you important information about the structures of the self-gravitating polytropic gas spheres. Okay, so that is the advantage of doing that. But here in the scope of this course, we are not really studying stellar structures, but I'm just telling that hydrostatic, which is a simple limit of hydrodynamics, what we are doing now, is also very, very important in certain aspects of astrophysics. Okay, so this type of thing is very interesting for studying stellar structures, stellar evolution. Okay, because this type of equilibrium can be thought to be one of the base phase of star forming cloud. Okay, star forming gas. Okay, so now we reproduced finally some hydrostatic results which we already knew, and we also said that how hydrostatics how the treatment of hydrostatics can be interesting in the domain of astrophysics, rather stellar structure. Okay, but now we will do a problem which is of utter interest for our course, and we will see that basically when we model, okay, most of the cases, and actually in some of the cases it may happen that the model is done the model is done assuming something, and finally it comes out negating or contradicting the basic assumption. Okay, so there is nothing to get disappointed for that. It simply says that we have to finally search for the reason for that inconsistency. Okay, so that is how one should do research. Okay, so people tried to fit hydrostatic model of solar hydrostatic model to solar corona. Okay, now for to know that, we have to know what solar corona is. So solar corona is nothing but the layer of plasma constituting the outermost part of the sun's atmosphere. So you all know that the sun's there is a photosphere, and just before above photosphere you can have a layer of plasma. So here you can see when in the total eclipse, the black thing basically covers everything up to photosphere, and after that this this thing which is basically like with a which has a burning type of structure. This is the corona. Okay, solar corona. Okay, so this is the layer of plasma. Okay, so we know now that in reality the plasma is actually as a this is corona is nothing but a flow of plasma, and so it's not only a flow. How to say that this is a dynamic action. So the corona is not static at all. So the corona actually it extends to millions of kilometers in outer space, that we know. But when we did not know about it, then people started they started different attempts to understand the several features of corona, and they started by fitting the simplest hydrostatic model of the model to fit to the solar corona. Okay, so just one information: solar corona in general can be seen only during eclipse. Okay, total eclipse. This is very fantastic view actually, and otherwise it can be seen using coronography. Okay, sorry, coronography. Okay, coronography is something another thing. It's related to coronary artery. Yeah, but it's a coronography. Okay, so these things are there. Now, this is a question for you to think. Do you know why we have to wait for a total eclipse, or we have to use coronagraphy? Why one cannot, see corona in naked eye or in, normal photography? Okay, so please think about that, and actually you can search, and if you find the answer, it's okay. If you want to share your answer and try to verify, cross check, you can write in the forum. Okay, now coming to the basic point. The point is that the solar corona has a higher temperature, and it is not like 1 or 2 times higher. This is actually roughly 150 to 400 times higher temperature than that of the solar surface. Now, sometimes even before that. So do you know maybe what is the normal temperature of the solar surface? This is nearly 6000 Kelvin. So if it is, of the like 250 times, so maybe you can think what can be the temperature of solar corona. It is you to calculate roughly. Okay, so now why this has a higher temperature, that we will discuss later in some other aspects if that arises. But here we now check that whether this corona, or rather coronal plasma, okay, here we are not talking, although we are talking about plasma, but we will just use normal fluid model. Okay, this is a very simplistic model. Okay, now we will check whether this fluid can be kept in a static equilibrium only under the interplay of gravity and hydrostatic pressure. That is the two things I was telling, right? The force balance for a normal fluid at rest is the interplay between the gravity and the hydrostatic pressure. So for a star forming gas, basically the self-gravitating force acting inwards, radially inwards, and it tries to make the system denser, whereas the counterplay is done by the hydrostatic pressure, which is radially outward, and thereby trying to reach an equilibrium. Okay, now whether always the equilibrium is reached or not, that's another story. That's the story of stellar evolution. That's also very interesting. Okay, so now here, as a first approximation, we will do two simple simplifications. One is that we consider spherical symmetry, although we can see that this is not quite spherical, but okay, yeah, roughly. And then also we consider this as a neutral normal fluid, although this is a plasma. Okay, but we will also see that at one point we will use some property of plasma. That is also important. Okay, so here basically we are trying to do some model. So according to the necessity of the model, we will do several things. Okay, so this is a schematic figure of the sun and the corona. So this is the photosphere roughly, or the solar surface, and this is the solar atmosphere, and this is the, so this is the outermost part of the solar atmosphere. So this is the corona. Okay, this part. And this is very reasonable to assume that the heat is produced in the lower layer of the corona near R0. Okay, so we are assuming that basically as the corona is hotter than the photosphere, then it is very reasonable to assume that something between the end part, the outer part of the photosphere, and the base part of the corona, somewhere some energy is produced, and that is responsible for that temperature, higher temperature of the factor 250 or something. Okay, let's say this is produced at a radius r0. This is the base of the corona. Okay, so to be very very honest, this is not exactly the photosphere, but roughly this is close to the photosphere, this part. Okay, Now you can also check the detailed structure of solar of a sun. There are several regions starting from its center. Okay, so radiation zone, convective zone, again radiation zone. So you can just see all these things. So this part should be clear, okay, when you are doing this type of studies. So then we will just think that this plasma or this fluid is heated due to some heating mechanism which is at this which is at this radius r0. Okay, and we say also, so at this radius we can assume that there is a furnace or a heater, okay, a burner, and that burner has a fixed temperature T0, which is a very high temperature. Okay, and this is giving energy. So the burner over here, this gives energy to this plasma. Okay. Now we also assume that the corona has a very small mass which experiences the gravitational field created by the sun. Now that is quite reasonable, because if you just see that this is highly dense, this sun over here, and the mass is super high with respect to the plasma mass which is just over here. Okay, so this is a good approximation that the mass of the plasma, which is over here, basically experiences the gravitational pull by the solar sun, excluding this corona. Actually, corona does not add much to the mass of the sun. Okay, so how much it can add, that is also a good question. Again, search in the internet for some estimates. So a very good way to learn astrophysics is to have estimates. Okay, if you know several type of estimates and order of magnitude, then you should, then you have learned actually 50% of the essentials of astrophysics. Okay, now so with this thing we can write the governing equations. Okay, and which should look like, now we are just eliminating rho using the expression of a relation of P and rho using ideal gas type equation. Okay, which comes from kinetic theory. So you can simply see that dp dr will then be equal to minus gm, this is the solar mass, this is a symbol for solar mass, g solar mass by r square times mp by kbt. Now m is the mass of the the plasma of this corona. Okay, and what is this? Simply, so this is nothing but n, and if you just see that, so this is roughly n, so number density. Okay, so once again, so I'm sorry, so this is not the total mass, this is the mass of one particle. Okay, sorry, in case it's confusing. Mass of one particle in corona plasma. Yeah, sorry. Yeah, so P by kBt, that is the number density of the particles, and this m times the number density gives us the mass density of the coronal fluid or the coronal plasma. This is the energy equation, ddr times kr squared dt dr is equal to 0. Okay, there should be 1 by r square as well, but this is 0, so 1 by r square will go there to get finally this one is 0. Okay. Now it is known from kinetic theory of plasma. Now you see we use some properties of plasma over here, that the thermal conductivity K of a plasma has a functional dependence of temperature as temperature to the power 5 by 2. So now remember when we were discussing about the the construction of the dynamical theory for real fluids. Okay, at one point I said that the K can sometimes have some explicit dependence on space. Okay, and actually it may happen that K sometimes has an explicit dependence on temperature, and that also finally solves the problem that K and T, they should not be considered as two different variables. K is most of the cases can be an explicit function of temperature as well. Okay, for example here. So finally then, using this zero divergence condition, you can have this thing. Okay, so r square t to the power 5 by 2 times dt dr is equal to a constant. Let's call this constant as k0. Okay, and if you now integrate this equation, you will have t is equal to t0 times r0 by r to the power 2 by 7, where t0 is nothing but the temperature, okay, for r is equal to r0. So as you can see, when r is equal to r0, then t is equal to t0. Now from this equation, if I ask you to tell me the temperature at r is equal to infinity or r tends to infinity, then you can easily say that at infinity the temperature is 0. Well, that is okay. That is quite reasonable. At infinity there is, so this is a hydrostatic, so if we are considering a hydrostatic model, then after a finite distance the plasma is no longer there, so the energy is not, cannot go there by conduction process, because the energy has to be has to go there only by conduction, right? It is not radiation. Okay, this is a conductive process. So t is equal to 0 simply says that the plasma cannot go until up to infinity, and that's completely true. That's completely consistent with hydrostatic model. So this is confined in a finite space, right? Rather, to be very precise, this one. Now we substitute this functional form in the equation of dpdr and we will see what happens. Now we will see, to our utter surprise, that dp by p is equal to minus this whole factor, which is a constant, times dr by r to the power 12 by 7. And if you integrate that completely just by using that at r is equal to r0, your p is equal to p0, then finally you will have the expression for the pressure to be this. And now if I ask you that what will be the pressure as r tends to infinity, well, as r tends to infinity, this term will be 0. So the pressure will be P0 exponential this thing times -1, because this is 0. Okay. So you will have a non-zero pressure. So pressure does not vanish at r at infinity. So that means that this is inconsistent with the static model. So what is the meaning of that? That means the static model, although it was good for temperature, but for pressure, the static model creates an inconsistency. And that's why Parker then actually correctly predicted that the corona is expanding. Okay, and not only the corona is expanding, this is expanding like a this is expanding also, from all the surface. Okay, and that is the, that we will see in the next lecture. Okay, next discussion. Okay, so that is the, that is the origin of different type of stellar winds. Okay, so for example, solar wind. Okay, so you see that an inconsistency in a simplified model could actually lead to a very deep conclusion about the existence of solar wind. Because it is true that nowadays we all know that solar wind, we all know that there is something flowing, plasma flow is there out radially outward from the sun, but beforehand people did not know, and that's why they did not apply the hydrostatic model just for fun. They applied it because for them it was the most reasonable one. But then when they failed, then they started to think otherwise. Okay, so in the next lecture we will discuss about solar wind. Okay, thank you very much.